All right, guys, welcome back from that activity. Now we're gonna go into data analysis. So we've been talking about this for the entire week, but um, essentially data graphs show us what happened. So the graphs you guys have just plotted basically just show the raw data that you collected in like a visual format, but analysis explains why that data even happened in the first place, right? So when it comes to ASEF, judges care more about patterns, reliability, and reasoning rather than just pretty charts because let's face it, like charts are great and all, but the actual value that these charts have is the analysis that comes from it, right? So the Google Sheets that we use today is just a tool to help your data be become visualized, right? So, uh, actually drawing analysis and drawing generalizations requires the extra intuition and that we're gonna basically just teach you guys today. So, um, some basic, I guess, structural thinking on how you can approach this is just saying if this increased, then this decreased, right? So if you're basically talking about thrust, like in the previous example, if the pressure decreased, then thrust increased, or vice versa. If the pressure increased, then thrust decreased. So that's just a very basic way of analyzing your data and getting meaning from your results. So we're going to go over some basic statistical analysis techniques that you can employ to analyze your data. So these are just some very basic definitions right here. So obviously mean is just the average value. Median is the middle value. So if you have a big data set and you just want to know what is one value that can kind of represent most of it, you can take the median. Standard deviation is a more advanced topic, but it basically explains how spread out the data is. And you can see this equation on the right side is the standard deviation equation or formula. You don't have to know it, obviously. You can put we're gonna show you guys how to actually get the standard deviation on Google Sheets, but you have to first understand what it means to have spread out data, right? So in any experiment that you guys do, the main goal is to actually decrease variability, right? You want all your data to be consistent and be as accurate as possible. So to do this, you might want to measure the standard deviation of your data, and that'll tell you how spread out the data is from the center or the mean. So you can see here if you have a small standard deviation value, so small SD, that means you have consistent results. That means your data is the way I think a better way of explaining it is that your methodology or your procedure of collecting data is very good and very reliable if you have a small standard deviation. On the other hand, if you have a large standard deviation, that means there's high variability in your data and you might have to improve your procedure or methodology. So that's why standard deviation I think is a good and I think simple way to analyze your data so that you know how to improve or how to go about analyzing your data. So, yeah, like I said, the goal in all experiments is to reduce that standard deviation. And you can see here, this is just a small graph showing how on the left side, you can see smaller standard deviation means that your data is closer together. So you can see the graph is a lot more narrow but close together. But a large standard deviation, on the other hand, has more spread out data and the graph is a lot more stretched out. The next thing that I think data analysis is useful for is showing uncertainty. So uncertainty basically just means we basically had these a bunch of data points, right? We're gonna go back into breakout room soon, and we're gonna have trend lines going through them. And once you do have a trend line going through your data, you can see how uncertain your data is from the predicted value. So you can see in this picture here, each data point is somewhat far away from the predicted data on this trend line, right? So all this is called error. It's called uncertainty. This I guess the distance from here to here, here to here, here to here, etc. So um some common sources of this uncertainty, so why this uncertainty actually happens, is measurement limits, environmental changes, or human error. So for example, if you were doing a research into how bacteria grows on a certain surface, you might measure the number of cells, obviously, on that surface over time. But if your temperature was not constant throughout the entire procedure, then it might affect your data and therefore give you uncertainty with your results. So that's just like an example for environmental changes. So uncertainty is obviously inevitable because we live in the real world. Stuff is bound to happen, but uncertainty honestly just boosts your credibility because it shows how you actually you applied the scientific method, you collected data, and you showed that there are some sources of error, but if you acknowledge those sources of error, then it actually boosts your credibility and it helps you present to judges a lot better. So yeah, if you ever get uncertainty, just keep that in mind. It's better, uncertainty is honestly better than having perfect data. So yeah. Okay, the last I guess topic that is under the umbrella of data analysis is correlation slash regression. So this is a really common topic that a lot of rigorous scientific projects cover. So regression and correlation just means that if you had two continuous variables, so in this case in our previous example we had pressure and thrust, right? So these are two continuous variables. You can basically draw a regression line through your data and get an approximation of your results. So that'll basically just look like this. So if you had your data and it looked something like this, right? You can have a trend line go through it, and it can basically just approximate all your results and kind of condense them down. So some tools for that is the correlation coefficient and the regression trend line, which we'll be teaching you guys in the next activity. The main thing that you guys need to know about correlation coefficient is that this R, if it's closer to 1, then that means it's a stronger relationship. If it's close to 0, then that means it's a weaker relationship. So if you're exploring like two different variables and how they affect each other, if your data shows that it's close to 1, that means there is a correlation, and that just shows that your data is accurate. However, if it's closer to 0, then it just means that it's a lot weaker and there's actually no relationship between the two variables, right? So you can see that here. You can see that when it's close to 0, the data is a lot more spread out and it's not really in like a neat pattern. But if you go closer to 1, you can see that it gets a lot, it becomes to turn into like a pattern, right? So in this case, it's just a line. In this case, it's a negative sloped line. So, um, yeah, that's R. Another common misconception with this term here is that it has to be close to +1, but it's actually meant to be close to the absolute value of R is supposed to be close to +1. So absolute value just means if you have a negative number and you take the absolute value of it, that just means that you're removing the negative sign and it becomes positive. So you can see here this is also a strong relationship, but it's negative. That's why R is -1. So yeah, that's just a common misconception that we have with correlation and regression. Um, so yeah, that was just a quick little lecture on data analysis. So now we're gonna go back into breakout rooms and analyze the graphs that everyone created.
Okay, everyone's back. Awesome. So on to conclusions. So this is, coming right after data analysis. Okay, so how to write a strong conclusion? There are three questions that you really want to answer with your conclusion, which are, what happened, why do you think it happened, and what would you do next slash future work. So some helpful sentence starters are, my data shows that, and you would have your result. This does not support my hypothesis because, and a possible reason is this. A limitation of my experiment was, and onto future work and things like that, you would kind of be starting to talk about next time. I would change whatever it is that you think could be improved. And obviously a new question I have is, this can be something that was prompted by your research that you wanted to explore more. So for an example from results to conclusion, so the project example will take the question, does room temperature change how fast ice melts? And the results are at 10 degrees Celsius, it took 32 minutes to melt. At 20 degrees Celsius, it took 21 minutes. And at 30 degrees Celsius, it took 14 minutes. So if you guys want to type in chat real quick, like what kind of pattern with the data do you guys notice? Like what kind of trend is happening with the time to melt? The higher the temperature, the lower the melting time? Yeah. Very good, very good. So you can see that, as temperature increases, the melting time decreases. And so, a strong conclusion would sound like my data shows that ice melted faster at higher temperatures. This supports my hypothesis because warmer air transfers heat to the ice more quickly, causing it to melt in less time. And then, next I will repeat the test with more trials and control airflow, like using the same fan setting to make the results more reliable. So you guys can try to, see how your data can form a stronger conclusion formatted like this. Um, for the question, why does this happen? If I'm doing an engineering project, do I explain my method or explain the data to say why my goal is met? You would explain the data that you've collected because the data that you've collected should be supporting like, your research question in some way.
So yeah, so we have like a little extra time. So we can just quickly go back into breakout rooms and we're gonna talk a little bit more in depth about research posters and we're gonna cover a small template that you guys can maybe use to design your posters.